So guys, welcome back. Today we continue with our lecture 21. We talked about 3.5, compressed sensing and matrix completion. What you're gonna see is some kind of magic, okay? Because things you cannot expect can be done mathematically. Let's go. So this is the basic outline of this presentation. I'll talk about the basic principles of matrix completion, and I'll talk about applications, and I'll talk about matrix application in the nuclear node. Okay. So the main problem we're dealing with is the problem you can often have in the industry, in fact, which is the case of incomplete data. So the basic principle, in fact, of compressed sensing is that a sparse signal can be exactly recovered from incomplete data. How come? So it is remarkable, in fact, it is a remarkable experience to see a perfect image emerging from too few measurements. A measurement, whether it's a medical image or in fact, a photography image. So in fact, mathematical analysis has identified the conditions on A and the minimum number of measurements needed to make something appear or emerge. So in fact, the sparsity in fact depends on the basis, as you've seen, V1, V till Vn, in which the signal is represented. And it uses, in fact, few V's. The signal here can be sensed in a different basis, which is we may call W1 to Wn. Okay? Here we're using the terminalities signals because, in fact, here the field from it came as a kind of field between electrical engineering, computer engineering, and medical applications. So we are trying to measure signals. Okay? But from our mathematics point of view, it's about just finding numbers, filling in matrices. The V's, in fact, are the columns of a representing matrix field, and the W's are the columns of an acquiring matrix W. A key requirement for compressed sensing is what we call incurrence of V and W, and the entries, in fact, of W2 times W, WT times VT times W are small. So those are, in fact, the inner products. So I'll go through the sensing, in fact, the mathematical stuff. So the sensing step produces, in fact, a number M, which is less than N, non-zero coefficients, and here it's about measuring, in fact, finding a Y, okay, which is completing a vector of signals, so of a known signal F, where Y is equal to FTW. So to construct F star, which is equal to Vx star, close to this F, we use the L1 norm optimization. So we minimize, in fact, we try to find an X such that the L1 norm of X is minimized, and X satisfies the equations WTV times X is equal to 1. We'll see a couple of examples. So in fact, this is typically a linear programming problem, and it tells us, again, to expect a sparse solution X star at the corner of the set of vectors. Of course, when we talk about linear programming, we immediately talk about the simplex method, which is a potential algorithm for locating X star. But there are faster ways, in fact. So this is pretty recent stuff. So in fact, Candice, Tau, and Bono theorem suppose that V and W are incurrent and X star is sparse. So it means that it has a number less or equal to S non-zeros. And the probability is overwhelming that if you have M, which is larger than C times S times log of N, the solution you can obtain will reproduce F exactly, which is pretty surprising. Okay? So the system, in fact, will have some kind of a noise. So we are trying to replace X that solves A equals to B plus A, where Z can be stochastic, of course. I'm talking about the noise and unknown. So the sparse problem is nearby, doesn't perfectly match the noisy. So what we want a stable recovery. So first of all, we solve the noisy data and obtain an X star. that is near the sparse X double star, which has a number less or equal to S non-zeros, and that would have come from noiseless data. So this conclusion is in fact true, where A had the restricted isometry property, for example, when delta is less than square root of 2 minus 1. So in fact, the RIP representation or the restricted isometry property, RIP is not for rest in peace, it's for restricted isometry property. It needs to satisfy 1 minus delta times the L2 norm squared of X is larger than the norm 2 of AX squared, which is larger than N1 plus delta times the norm 2 squared of X, okay, if X is sparse. So this is here we're trying to find X as a vector. Okay, so now this generalized to what we call the lasso noise. So fortunately, in fact, the matrix A can have columns also chosen randomly on the unit sphere or chosen randomly from the normal distribution, the Gaussian distribution, or with independent random entries. Okay, just bounded by plus or minus 1 over root of m in another random ways. So the RIP requirement is almost surely satisfied if or m is larger than Cs log of n over s. In fact, this finally connects the number of measurements m with the sparsity s. And the nosy that leads us to replace basis pursuit, where ax exactly equals b with lasso. So in fact, the lasso with noise is to minimize the norm 1 of L1 of x under the condition that the norm of ax minus b, norm 2 of ax minus b is less than x. So we're trying to minimize the noise. Okay? So let's see an application. In fact, in MRI, magnetic resonance imaging, this has been used by on what we call the Logan chip, which is a kind of test image, which was corrupted by noise. So in fact, what it looked at before, it looked at that as if the magnetic resonance imaging MRI had been stopped too soon. Okay, so you had an incomplete image. So to improve the image, what Candace did, he tried an idea using the L1 minimization. But to his surprise, in fact, the phantom image he got before, which was incomplete, became perfect, even though the data was incomplete. Okay? So it was almost an online equivalent to the Bingen's discovery of X-rays in 1895 as an accident that gave birth to this industry of MRIs and compressive sensing. So in fact, compressive sensing has accelerated MRI scan times from 8 minutes to 70 seconds with high quality image. Okay? And even it has a strong impact on also on dynamic imaging, which has became feasible even for small children. Okay? So you don't expose the children a long time, like 8 minutes, to this magnetic resonance devices. Okay? So it had, and you see how math can bring to humanity some kind of strong achievements. So now let's talk about sparsity. The rank of a matrix is like the number of non-zero. This is a mistake in a vector. In some way, the rank measures sparsity. So for low rank, the matrix sigma. So guys, if you didn't understand what came before, it's not a problem. But my point is to make you understand this part. For low rank, the matrix sigma of singular values is literally sparse, are non-zeros. Just as the number of non-zeros is the zero norm for vectors, the rank is a zero norm for matrices. But the norm V0 and A0 are not true vector in matrix norms. So for example, if you say that the norm V0 is equal to 2 times the norm to the norm 0 of 2V, and rank A is equal to the rank of 2 times A. Okay? So multiplying by 2 doesn't change the count of non-zeros or the rank, but it always doubles any true norm. Okay? So nevertheless, we often want sparsity for vectors and low rank for matrices. So this is to reach the fact that when we talk about sparsity for vectors is exactly the same as talking, or almost the same as talking for low rank about low rank for matrices. So the matrix completion problem starts with missing entries in your matrix, your data matrix A0. Okay? So we have here a couple of examples. We are fortunate, we can see some kind of examples. So what we want is to complete A0 to A, keeping the rank as low as possible. So this is our mission now. You got it, guys? You have an incomplete matrix of data, and you want to complete it and to make to obtain the lowest rank possible. So we are introducing what? A minimum of unexplained data. And this problem of missing data is widespread, in fact, in all areas of observational science. So some assumption is needed to fill in the blanks and minimum. Three simple examples. You have three simple matrices: A0, B0, and C0. And what we can do, if I have the idea that I'm filling in A0, what is the lowest rank I can have in A0? It's 1, right? Am I right? So one of the possibilities is to, for example, here. So this is the observation. All can be completed with rank 1. For example, 0 allows any multiple of 1, 2 here. So you can put, for example, 2, 4. Okay? Or 3, 6. Got it? B0, for example, if you want to complete it and make it rank 1, it allows any number B and C which satisfy the condition that BC equals 4. Okay? You don't want to rank 0, you want to rank 1. So the condition that BC equals 4, for example, if you put 8 half, it works fine. So you can put here 8 here and half here, and you can see you have a rank 1 matrix. While C0 allows only 6 in its last entry. Okay? You can see that if you put here 6, you can get a rank 1 matrix. Right. So in fact, what we can do here to get this lowest rank, we can work with a nuclear norm. With vectors, we relax the sparsity using the zero norm, okay? Or the L1 norm. With matrices, we relax the rank norm using the A0 norm to the nuclear norm, AN. And this nuclear norm is the L1 norm of the diagonal of this sigma. So in fact, all comes back to using the SVDs. So we are minimizing the sum of the singular values, which is the nuclear norm. Okay? So now we have what we call convex norm, but not strictly convex because we have a kind of triangular inequality to satisfy. And in fact, the example matrix B0 could be completed symmetrically by any B equals C between -2 and 2 in the previous example. And the nuclear norm Bn stays at 5. You can give me just 2 more minutes, guys, I will finish this. So a famous example, for example, with Netflix, of course, you all know Netflix. A famous example for matrix completion with the Netflix competition was that the ratings of films by end viewers went in a matrix A0, but not all customers did see all the movies. So many ratings were missing, in fact. And those had to be predicted by a recommender system. So what the competition gave is that the nuclear norm gave a good solution that needed to be adjusted for human psychology. Okay? And in fact, well, it was, in fact, just a challenge, not for imitation. In fact, Netflix was not originally a pure mathematics. Another application, just to finish, is to work on sampled data and compute the covariance matrix from a lot of sampled data. Of course, computing all covariances can take a lot of time, and in fact, minimizing the nuclear norm based on subject to a set of conditions, a good solution. So I'll stop the recording now. We'll continue with this next.